All right, quick review where we are so far. If you go to github.com/nandland/SPI-Master, you can check out this code. Go to the Verilog section for the Verilog code. The source code, as well as the simulation code, is all available here. So you can check out the actual code. The last couple videos, we introduced the SPI Master with no chip select, and we simulated it. So we went into EP Waveform Viewer by going to this URL here, edaplayground.com/x/5 lowercase h capital C 6, and simulating the test bench, simulating the actual design for the SPI Master, and things look good. So now let's add in this chip select functionality, which I mentioned is going to be instantiating our SPI Master and adding some more stuff around it. So we can, this module is going to support arbitrary length byte transfers. So we can do chip select low, send 1 byte, chip select high again. We can do chip select low, byte by byte, chip select high. Very flexible, and you can change it too. So you can do send 1 byte, send 3 bytes, send 5 bytes, and you can change that on the fly. It's not like you have to predetermine that at compile time, which is pretty handy. It supports all SPI modes as well. We have a couple input parameters. SPI mode you're familiar with, clocks per half bit we described in the last video. These two are new. So max bytes per CS, this is the maximum number of bytes per chip select you'll request. And the reason for this is just to specify the width of some counters and things like that. So if you know you're not going to ever do more than 16 bytes per chip select, set that to 16, that's fine. If you think you might be going up to 128, 1024 or whatever, it's not going to explode the number of flip-flops of this module by too much, but it will just allow you the counters to get a little bit bigger. CS and active clocks, in case you need to hold chip select high before the next command is allowed. Sometimes some components require some inactive clock time. Some chip select inactive time. So chip select needs to be high for 200 nanoseconds between bytes, for example, for your ADC or for your I/O expander or whatever chip you're interfacing to as a slave to actually work correctly. Some of them require that, so I put that in here. You can set it to 1, and that it'll work fine if you don't have any requirements, but this makes it a little bit more flexible. Okay, so what's different here on this module interface? We got the same SPI interface, except now you'll notice we have this O SPI chip select n. So the lowercase n means active low. These three are the same as the SPI Master. We also have TX byte and TX data valid. Those are the same. However, and TX ready too. These three are the same. However, we added this ITX count. So now, excuse me. This is when OTX ready goes high, we can set the TX counter to the number of bytes that are going to be sent in a particular chip select. So keep chip select low, set that to 3, for example, and it'll wait for 3 bytes to go to be pulsed on this input before the chip select goes high again, indicating that you're done. On the receive side, you have the same ORX data valid, ORX byte, but I've also added this ORX count, which is an index. So if you're waiting for 3 bytes to be received, ORX count will be 0, 1, 2, and then you know you're done. So here's some basic signals. Here is the instantiation of the SPI Master. Again, this is just wrapping some extra functionality. So basically controlling chip select line using a state machine is the extra functionality around the SPI Master that didn't exist before. And again, just to reiterate, the purpose of this is some ADCs, some DACs, some external chips just don't need a chip select. And so maybe you just want to use your SPI Master and you don't care about what I'm about to talk about, which is fine. Most do use chip select, so you probably care about what I'm about to say. So chip select is controlled using a state machine. I like state machines. I think they're easy to follow. It's easy to understand where the flow is rather than trying to keep counters and messiness. So you start off in idle. When you're in idle, your TX is equal, so your TX ready, indicating that you're ready for something to happen, is going to be a 1. So when you're in idle, it's going to be a 1. There's other cases in which it might be a 1 as well, but idle is the main one. So let's go back. All right, so you're in idle, and if your chip select is high and data valid comes along, so there's a data valid pulse, then that indicates that the start of the transmission is happening. So we're about to start sending some data. So what do? We're going to register in the RTX count. Again, when you get a data valid pulse, I like to register inputs to local registers inside of a module, so that if the higher level module changes the ITX count, for example, it won't mess up the functionality of this internal module, this internal code. So I register that. I'm going to drive chip select low, and then we're going to go to the transfer state. Transfer. Next clock cycle, we're in here. And it basically says we're waiting for master to be ready. So the data valid pulse, this data valid pulse here, when we were in idle, also kicked off the low-level SPI Master and made it start. So the SPI Master is now transmitting on the line. And when the SPI Master is done transmitting, it'll drive master ready high, which is an output of the low-level master. So master ready goes high. So the master says, nobody's using me right now. This higher level module then sees that and then looks to see, is it done? Is it done with a burst of SPI transactions? And it knows that by looking at this RTX count. So if RTX count's greater than 0, then it's not done and it needs to do more stuff. And then if it's equal to 0, then it is done and we can go to this state here. But if it's not done, it just waits for the next data valid pulse to come along. If data valid comes along, it'll decrement that counter and the master will work on the next byte. So say it starts at 4, RTX count starts at 4, it'll be 4, 3, 2, 1, and then 0, and it's done. The higher level module does need to keep driving the data valid to put the next byte on the line. When it's done, we're going to drive chip select high. And then we have this state for inactive counts. So this is the ability to drive inactive counts to some variable number. So we register that based on the input parameter. And this is another counter. We jump down to this inactive state. As long as the inactive count is greater than 0, I usually just count down, generally. So we count down from inactive clocks. When it gets to 0, we're done. We go back to idle. And when we are in idle, we need to report that we are ready. Which we've been doing, as we already talked about that. There's another time you report idle, which is when you're in the transfer state and master is ready and your TX count is greater than 0. And you're also not currently sending something. So you're in transfer, you're in the middle of a burst of bytes, so sending 5 bytes, you're in the middle of that. Your master has reported that it's ready, and your TX count is greater than 0, so you have more stuff to send. Then you want to tell your higher level module, your transmitter is ready, so send me the next thing. I'm ready for it, and it'll ship that next byte out. So it's pretty straightforward. You got a pretty simple interface here with your chip select added in. You don't need to worry about manually driving chip select, which is great. You can just say, I got 5 bytes to send, boom, 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 here they are. And it works just like that. RX count. I didn't talk about RX count. RX count is really, really simple. So if your chip select is high, you can reset your RX counter, because chip select being high means that nothing's happening on the line. Otherwise, if you get some RX data valid out of the master, then you can increment your RX counter. So it'll start at byte 0, byte 1, byte 2, byte 3, and it'll count up for every byte that gets shipped off on the transmitter. So that's it for the SPI Master with chip select. The next video is going to be looking at the test bench for this particular piece of code, and we're going to be using the EDA playground again. Got it. Hi, kitty. Meow, go away. So we're going to be using the EDA playground again to simulate this code and take a look at the waveforms, make sure everything's looking good. Hey, I just wanted to jump in at the end of this video real quick to say, please check out patreon.com/NANDland and consider supporting me there. I would really appreciate it. It helps me cranking out these good tutorials and these videos. So if you found this valuable, consider heading over to Patreon and supporting me. Keep me making good content. In addition to that, please consider getting yourself a Go board so you can actually program this code and try it out on real hardware. They're available at nanland.com. And thanks for your support.